Welcome back to chapter 12 in our book. This is the third and final chapter in Unit 3, looking at gathering data. We've already seen randomization, we have seen simulations, we have seen surveys. Now, this chapter we're going to be looking at experiments and observational studies. There's going to be some process stuff in here. There's going to be some vocab in here. There's going to be very little actual, like what we would consider math in here. This is where we get the numbers to do the math on. So, we're going to be looking at, again, experiments and observational studies. Hopefully by the end of this, we'll be able to identify each of them and the different parts of each of them, and also to make some. So an observational study first is just where you're observing a situation. You don't assign choices. This choice assignment is huge, and that's the difference between experiments and observational studies. So observational studies, you would let people self-select their groups, which might be in a natural thing. It might be in a designed thing, and they just kind of self-select. Um, things here, we could be looking at um, grades for um, calculus A, B, and calculus BC. It's like, people self-selected to go into calculus BC as opposed to AB. As opposed to if we were looking at grades between, say, like my third period algebra and Mr. Schmidt's third period algebra class. The people were randomly assigned into those classes. So if you choose, or if the subjects, the people choose their groups, it's an observational study. And so there's a couple examples in the book. One of them, and don't forget you're reading the book. This is a good chapter to read. There's a lot of details and minutia in here, and some great examples, and some really funny comics as well. I love the PhD comics. They're great. I have some of them on my wall, and I've seen a lot of these, but this one had a bunch of good ones. Anyway, so there's an example between the music education and grades, but they didn't assign the students to get the music education, and so you can't tell. It's like, oh, well, the people that take music are better in math. Well, are they better in math because they take music, or do they just both happen to be in that same group? Um, and so um, it's called a retrospective study because it wasn't done like in real time. They looked at the past data. The data was all there for them. I mean, they were able to see what students took music and what their grades were, and so they just looked back and saw it. So that doesn't make it good or bad or anything. It's just that's what the retrospective part of it is. Um, and then if they were doing it like in real time, it's called a prospective study. Then observational studies are valuable because you can discover trends. We can say like, hey, students that are in music do better at school. It's great for advertising. Hey, if you people that like this kind of thing also tend to like this kind of thing. And so it does make those connections, but it does not demonstrate cause and effect. And a lot of times we're looking at demonstrating cause and effect as well. In order to do that, you need an experiment. And an experiment, it allows us to prove that cause and effect relationship. It is possible to prove it without an experiment, but it is very, very difficult. Um, there are a couple big cases like smoking causing cancer. That is a big case that has never had an experiment done on it for a variety of reasons. The time, the ethics, just the logistics of it does not lend itself to an experiment. But there's been so much observational evidence for it that they were able to establish a cause-effect relationship. Um, so, but the key point of an experiment is the experimenter must identify at least one explanatory variable, called a factor, and manipulate at least one response variable to measure. And then they randomly assign groups. An experiment imposes a treatment. The experimenter says, you're going to take this, or you're going to do this. And then the subject actually has to do that, or take that. I mean, that's part of being in the experiment. So, an experiment, they manipulate factor levels to create treatments. Factor levels could be the it could be the level, like the amount of a drug that's being taken. It could be the type of drug that's taken to do whatever. Um, it could be the amount of water that you're giving a plant. It could be the amount of a little supplement in the water that you're giving a plant. It could be whether or not there is a supplement in the water that you're giving a plant. So the factor level is just the amount of something that you're changing. Randomly assign subjects to the treatment levels. That randomization is huge. That's the difference between an experiment and an observational study, really. Because the observational study, the people self-selected. The randomness you select, which is important because the people that go one way, like for the music, if you're looking at music and math grades, well, people that are good at math might self-select to be in music as well. And so that random assignment is huge for an experiment. We'll talk about that in a minute. Then it compares the responses of the subject groups across the treatment levels. So there's that comparison there. And then the experimenter actively and deliberately manipulates the factors. You get a certain thing, that is, like this plant is always going to get 3 teaspoons of water throughout the life of the experiment. It may be good, it may be bad, but that's what it's getting because that's where the data is going to be. And then the experimenter observes the response variable and compares responses for different groups of subjects who have been treated differently. 3 tablespoons of water wasn't quite enough for this type of plant, but the half a cup of water was. Then some vocab. The experimenter is experimenting on experimental units. That's the stuff inside the experiment. However, people don't generally like to be called experimental units, so they tend to be called subjects or participants. The value the experimenter chooses for factor are called the levels of the factor. And then a treatment is a combination of specific levels from all factors that an experimental unit receives. Sometimes it's one thing, like it could be just like the amount of water a plant gets. Or maybe it's a water and a type of fertilizer, like you can do a combination of things, and we'll see some of that in a few minutes. Experimental design has 4 huge principles. The first one is control. The control is trying to control all the different pieces of all the different things that might affect the outcome, so that the only thing changing are the treatments, because then we can say that the change of treatment is what caused the change of response. So we need to try and control every possible thing about an experiment. Now, is that entirely possible? Not usually. There's usually some stuff that we're not thinking about, but we'll get to those in a minute. The randomization. that helps to control some of those other things that we don't know about. Um, for instance, certain people might react differently to certain treatments. By randomizing, that's going to spread that variability out between the treatments. And so that helps to control those individual responses. Um, and then without randomization, you don't have a valid experiment. Randomization is huge. Um, I know we'll see it in a little while, but one of the things that gets people is they'll say that since the subjects were volunteers, it wasn't a good experiment. That's not true. Most experiments do work with volunteers. You then randomly assign the volunteers to treatment groups. So it's not like a survey where you can't have volunteers. Like you have to ask everyone. Um, because of that randomization, that takes care of that. Um, but you have to have volunteers because otherwise, I mean, you can't just randomly select people from the population and say, "Hey, we're going to experiment on you." That doesn't generally work out well. Replicate. You can't do it for just one thing. You have to have multiple participants in every treatment group because you might have a fluke. You might have, I mean, there's lots of things that can happen. So you need a sample size big enough to make a generalization. And we will be talking about that sample size. And we'll be getting margins of error. Like we got to see a lot of margins of error recently because there's been lots of polls and stuff in the news. And so we'll figure out what we can do to make a margin of error that we want. And then blocking. Blocking is not something that has to happen. It's basically the same thing as stratifying because with blocking, um, you can see different groups and how different groups might react differently to treatments, and you can actually compare inside the groups. That's not the main focus of blocking, though, especially not in AP statistics. But what blocking does is it means that you get um, an equal representation from each of your groups into each of your treatments. So certain things might work better on certain groups. Like you might block on gender or even race, because sometimes the different races will react differently to different types of treatments. You could block with like plants if you're trying a fertilizer. Like, well, we'll see one in a minute, where we have some plants from store A and some plants from store B. And so we're going to have a store A block and a store B block. That way we make sure that each of the plants from the different stores get equal representation in the treatments. And that can be important because maybe store B has a better quality of plant than store A does. And so they're going to react better regardless of what treatment they get. So the blocking helps spread that variability out. Um, And then notice this is not required. Unlike the other three things, the control, the randomization, and the replication are absolutely required in an experiment. The blocking is not required, and it depends on the situation. So some diagrams. Whenever you do an experiment, you do need to write a diagram. This gets you points on the AP test as well, believe it or not. And this is basically the diagram. It'll have slightly more detail, such as our random allocation. We have, say, um, we'll just go 12 tomato plants, and then it gets randomly associated to 6 in group 1 and 6 in group 2. Treatment 1 is half a cup of water per day. Treatment 2 is the 1 cup of water per day. And then we compare. So you wouldn't like say treatment 1, treatment 2. You would actually have it defined. Now you could have it defined separately and then have treatment 1, treatment 2. especially um, if your treatments were a little bit more complicated, um, where you wouldn't want to just like write it out right in a diagram. Um, you could use treatment 1, treatment 2, treatment 3, etc. Um, and so then we get a difference. Well, is the difference a big enough difference to matter? Sometimes, it's like, yeah, there's a difference, but it's not very big. When it's big enough to matter, it's called statistically significant. And there's a great comic in the book on this one specifically, and it's one of my favorites, um, where the person proves that she's his statistically significant other. Um, but when it's called statistically significant, it means that the differences are larger than we'd get from just the randomization. And generally speaking, throughout the rest of this year, we're looking for statistical significance. Um, and we'll be talking a lot more about that later on. Um, so now it's just we want to know if it's like big enough to matter, or if it's like super small, like that. That's easy. And good um, there's a good graph in the book that helps to demonstrate that too. Um, so experiments versus samples. So they both use randomization to get unbiased data, but they do so in different ways. And I mentioned this earlier, but the sample surveys, they randomly select from the population. Experiments, usually done with a pool of volunteers, which, that can create its own difficulty. I know in the past on the test for this, we've had a question where they were looking at a medication to stop hangovers. And, so who's going to volunteer? Well, probably people that drink a lot. Well, are they going to be affected differently than the average population? Maybe, we don't know. But those are the volunteers. But by randomly assigning the volunteers, we hope to try to control a lot of that stuff. Um, so we get the volunteers and we randomly assign them um, to the treatments. And whereas from the population, we get like a little subset of the population. When we have volunteers, we try to use all the volunteers. So you have a population of like 20,000 and you sample 100 people. You have 50 volunteers, you use all 50 volunteers. Um, and then for control treatments, um, a control is where, like, that's the standard. So that would be either you do nothing. So like if you're seeing like if a certain drug affects a headache, well, you could have drug A, you could have drug B, or you could have nothing. The headache's going to go away on its own. And so this just it helps give us that standard there. Sometimes nothing doesn't work. For instance, if you are um, using plants and you're like testing the amount of water, well, if you give a plant 0 water, it's not going to grow. That's not a good baseline. And so in that case, a control wouldn't necessarily work out so well. Um, but it's whatever the normal is what um, the baseline is. So if we were looking at, say, we have a supplemental um, like assignment. Oh, the study plans. We have the study plans. We want to test to see if the study plans help people. Well, I would randomly assign you into 3 groups. One group does all the study plans, one group does half the study plans, and the other group does none of the study plans. But every group would still do the assignment. The assignment would be the baseline. That would be the status quo. The study plans are the extra. And so that way we could see if doing the study plans would help. Now, that would be an experiment that I couldn't really do because telling people that they can't do the extra stuff to help themselves out, um, that wouldn't be particularly ethical. And so that's where an experiment doesn't really work out. I'd have to use an observational study for that and see like, oh, hey, the people that do the study plans tend to do better on the test, which is actually true. Now, are they doing that because the study plans are easier because they already kind of got it, or are the study plans helping? We can't establish that cause and effect. But we can observe the trend that, hey, the people that are doing this stuff do better on the test. Um, and so that's a control treatment. The group is called the control group. Um, Blinding. So blinding is when you don't know who has what treatment. Generally speaking, the subjects should not know what treatment they have, because if you know what treatment, like if you think you should be getting better, a lot of times you get better or do better. Um, if you're a tomato plant, it probably doesn't matter so much. And so that's what's blinding. Like they don't know what group they are in. Um, and so that could be a group that includes the subjects or the treatment administrators, technicians, things like that. Or it could be the people doing the judging and the calculating and stuff. When both groups don't know what group people are in, that's called double blind. That's the way it is, generally speaking. I remember there was a great episode of House where Dr. Foreman, and I can't remember his girlfriend's name, but she had um, early stages of MS, and they were doing a clinical trial to see if this new drug could help stop the onset of that. And she was doing better. She was doing so much better. And then Foreman, the doctor who was in charge of it, um, found out that she was on the um, she was in the control group, which meant she was getting a placebo, which we'll talk about in a minute. But like her treatment was basically not doing anything medically, but she was getting better. And then all of a sudden, when he found that out, he started treating her differently because it's just a placebo. And so that ended up actually causing her to be thrown out of the experiment because now she knew and he knew, and it was bad. But people do treat other people differently when you think that they're supposed to be doing better or not. Um, and so that's people in both cases are double blind. Now there are people that do know who's in what group, and they assign like get everything set up, but they don't have any contact with the groups to speak of. So here's the placebos. So that, as I said, like if you think you should be getting better or doing better, chances are you do. And so to counteract this, the people in the control group generally get a fake treatment. A lot of times it's called a sugar pill. Um, it's a placebo. And so here you have this medicine A to help a headache, medicine B to help a headache, and the control group gets a unflavored Tic Tac. It's not going to help a headache. There's nothing in there that says it should help a headache. So that just helps to get rid of that psychological impact of taking something and thinking that you should be doing better. That's the placebo effect. It just talks. That's the what we were just talking about. So the best experiments are randomized, comparative, usually double blind. They have a control group, which is a placebo or a standard treatment. So if you're testing a type of fertilizer on plants, the you have the levels of fertilizer. The control group is none. Blocking. Um, so when experimental groups are similar, we block them. um, or we can block them. It's not essential, and that isolates the variability due to the differences between the blocks, whatever those might be, which spreads them out across the treatments so that they can be taken into effect. That's called a randomized block design. And so this is what a randomized block design looks like as opposed to the other design that we saw. Now here we have 3 treatments instead of just the 2 treatments that we saw in that very simple one. But notice we have the 12 tomatoes from store A are going here. The 12 or 6 tomatoes from store B are going there. And then each of them gets randomly assigned to a treatment. Notice we still only have 3 treatments here. That is not 6 treatments. It is only 3 treatments. It's just we get a treatment from store A and we get a treatment from store B. And then we compare, and then a lot of times we'll compare from there as well. So again, notice we only had 3 treatments, not 6. And the goal is each treatment group has representation from each. That way we didn't get all of the store B tomatoes into treatment A. Because again, like store B might have just a better quality tomato plant. And this way we can isolate the effect of the fertilizer to eliminate any store A versus store B differences because we're looking at the fertilizer, not where the plants came from. Retrospective or prospective study, subjects are sometimes paired because they are similar in ways not under the study. Matching students in this ways can reduce the variability in like blocking, and this is called matched pairs. And when we're looking at matched pairs, we look at the difference between them. So sometimes things get paired based on the similarities, like, hey, this is very similar to this. People say identical twins are the best match pairs. Not exactly. The best match pair with someone is that person. Things where we'd use match pairs would be pre-test, post-test. Like I wouldn't take the average pretest and the average post-test and compare them. I would take each person's individual pretest and post-test, see how much they improved from the pretest to the post-test, and I would use that data. I had someone do an experiment. They were using different types of shoes running on the track to see what's fastest, and they had a bunch of their friends, and each of their friends ran using the different types of shoes and then compared the data amongst just that own person because some of the people are going to be faster than the others regardless of what shoe they're wearing. And so they weren't comparing with each other, they were just comparing with themselves. And so that's matched pair. That doesn't always work out, but sometimes it does. So blocking is the same idea as stratifying. You both block in groups that are similar to remove the unwanted variation. And we use blocks to reduce variability so we can see the effects of the factors, not usually interested in studying the effects of the blocks themselves. Sometimes we are, but not usually. But specifically in AP statistics, as I mentioned, blocking is used to reduce variability within the treatment groups. That's big. There's almost always not almost, like in the free response there's 6 questions. I'd say probably a little over 50% of the time there's going to be a question on blocking, like a part A, B, or C type question. Adding more factors. We can include multiple factors in the treatments. I had mentioned that. We're going to see here. So we do have 6 treatments. We have the fertilizer, which could be control, half dose, or full dose, and then notice control, half dose, full dose, and then water. We don't give them any water, or we do give them water. So the two the 3 levels of one treatment and 2 levels of the other treatment makes 6 total treatments. But notice we have all the combinations. We wouldn't do control and no water and then fertilizer and water, because then we couldn't tell, like, well, was it the fertilizer or the water that made the difference? Um, and so when they're associated um, with the levels of another factor, we say that the factors are confounded. So that just means that we don't know what one is necessarily causing the effect. They might both be causing the effect, so it's not one or the other. Um, but that's confounded. They're called confounding variables, and we just can't separate out the effects. Confounding comes about when you have all sorts of factors um, that have an effect on the response variable, and generally speaking, that's true. We try to limit that as much as possible. Like if we were growing plants, we try and put them so they had the same sunshine, they had the same air quality, they had the same everything. But, there's just some stuff that you can't control, some stuff that you don't even necessarily think about. So confounding variable is that third variable that just gets into the experiment. Um, and so we're trying to measure how the factors affect the variables, but when that when a confounding variable gets in there, it just makes it difficult because we can't tell what it is. That's where that control is so important. You want to try and control everything possible. Um, and so, example here, we want to see if detergent A cleans better than the detergent B. So we use a washing machine with detergent A and another one with detergent B. But then, was it the detergent or the washing machine that caused clothes to get cleaner? That would be an example of just bad control that added a confounding variable. If you wanted to figure it out, you'd need to use the same washing machine a few times. Um, and lurking variables are just those other variables that are out there that might be confounding. They're things that we need to think about, like what else could be affecting the system. Um, And so sometimes seeing what they are can be difficult. Sometimes it's obvious, but hopefully when they're obvious, you can control for them. But if you can't specifically, you generally want to um, discuss them. And so the lurking variable has associations with both x and y that makes it appear that x may be causing y, even when it's not. Um, I know my example of the shark attacks in Florida increasing at the same time as the ice cream sales in Chicago. Lurking variable would be the changing seasons and the heat. It's summertime, more people are going swimming, more people are buying ice cream. Um, it doesn't mean that one causes the other, but they're both caused by something else that's affecting the system. Um, and so a confounding variable is associated in a non-causal way, which means it's not necessarily causing a um, it's not causing the results, but it might be helping, and we don't know. It's like they're working together. They're both going towards um, the same thing. And blinding um, is a way to try to um, help with the confounding because it just makes that extra level of randomness. So, what can go wrong when you're doing experiments? Um, just because you can't run an experiment doesn't mean you can't study things um, to get those trends. Always be aware of confounding, like that. Like when you're doing setting up surveys, you're constantly trying to get rid of that bias. Confounding is like bias in an experiment. You're trying to minimize it as much as possible. Um, bad things happen even to good experiments. I mean, things can happen. Sometimes you get flukes, sometimes you're just recording all the wrong stuff and you're missing the big picture. Um, Lots of stuff that can happen. Don't spend your entire budget on the first run because you might not see a lot of things. You might get like halfway through an experiment and think, oh man, I wish that I would have done this instead. So do a small one first. It's kind of like doing that pilot survey to see if you get any responses that you weren't expecting. Then you can adjust for that. So, what have we learned? Hopefully you can recognize sample surveys, observational studies, randomized comparative experiments. They collect different kinds of data in different ways. Um, Identify retrospective and prospective studies. So did it already happen, or are you collecting the data more in real time? Um, Only use well-designed experiments can allow us to reach cause. Only well-designed experiments can allow us to reach cause and effect conclusions, which is huge. That's what we're really trying to get. So we have to manipulate the treatments. We have to randomize. We have to control those variables. Um, the the principles of experimental design. Control as many variables as possible. Random assignment helps actually to control a couple more variables. Replication, you have to do it more than one time. You need more than one thing in a treatment group. And then blocking is the fourth one that's not necessary, but it can help us to control some more of those variables. So we have the value of a control group and placebos to help control the placebo effect, and then recognize problems posed by those confounding variables and stuff. Some AP tips, as with stratification, make sure that you justify your blocking according to the parameter of interest. That is huge. Blocks are to ensure that variability is reduced, not to create more groups to compare. That is something that is a common mistake on the AP test when they ask that question. Right, specifically and in detail. I know when we do those AP practice problems, one of the most common reflections is that you need to include more detail and better descriptions. Then usually one of the 6 multiple choice questions is focused on, usually one of the 6 free response questions is focused on survey or experimental design. Generally speaking, it's question 3. Every once in a while, question 2. But one of those is going to be on this because surveys and experimental design is one of the 4 big parts of statistics. We have data analysis. That's what we did before this. Survey or data collection, that's this. Probability, which is coming next. And then inference, which is the last big chunk of the class. So there will be a question. That's why we have so many to choose from, because there's always one. Don't be confused by double blinding. There is an assistant that sets everything up. So somebody does know what's going on. It's not just random and nobody knows. And then surveys and observational studies, we can conclude that we have an association. With experiments, we can have cause and effect. And key difference between a survey and experiment is that in an experiment, we apply a treatment. You impose a treatment. You say that you will do this.